Hi, this is Kevin Trainer, and welcome to part one of my lecture on chapter 11 of the Zelle 3rd edition Python book. And in my class, we don't cover three sections of this chapter: 11.4, 11.5, and 11.6. These are all interesting, kind of graphically oriented examples that draw on chapter 4, which we don't cover either. So the lecture is not going to cover them. So, what does that leave us? Well, that leaves us two kinds of data collections. And data collections, that's what the chapter is all about. And the first kind is one we've already experienced before. It's lists. Okay? And we're just going to learn a lot more capabilities of lists and see some applications of them. And then when we jump to section 11.7 in part 2, we're going to be talking about dictionaries. Okay, so that's what's coming. Let's get started. I'm not going to, as is typical for me, I'm not going to read through the objectives. I'm going to leave those for you. Okay, now this is a chapter that has, one could argue, a lot of math in it. Okay. But we're not going to duck the math this time. We're going to jump right into it. And why is that? Well, because I think it's useful math in that it's statistics, pretty simple things like mean, median, and standard deviation, which I think are important for anybody who wants to be literate about data science. So even if you don't want to be a computer scientist or a mathematician, if you're in the information science field like we are in my classes, well, then I think you want to know about these things. The other reason I'm doing it is it's really a good example of how you can take the parts of the math that you like the least and hide them in functions. Okay, so it's sort of a lesson in math defense. Okay, and of course, if you're a math major or you love math, well, you're going to love this just because it's math. Okay, so the example problem we're going to be dealing with is simple statistics. Many programs deal with large collections of similar information: words in a document, students in a course, data from an experiment, observations of some kind, customers of a business, graphic objects drawn on the screen, cards in a deck, in some kind of a game. Okay, so in chapter 8, we created a sentinel loop to calculate the average. Okay, and this is the exact code from the example program called Average 4 in chapter 8. So let's say we kept the sum, we initialized it to 0, we had the count, we initialized that to 0. We prompted the user for a series of numbers, and then in the end we calculated the average. And you'll remember that I pointed out that we should have really checked and made sure that the user didn't tell us on the first entry that they didn't have any data for us, because this program it's good because it fits on the slide. It's bad because it's going to divide by 0 if you don't give it any input. And of course, we wouldn't do that, meaning you and I. Okay, let's go a little further. So the program allows the user to enter a sequence of numbers, but the program itself doesn't keep track of the numbers that were entered. It only keeps a running total, which for an average, a basic mean, that's all you need. Suppose we want to extend the program to compute not only the mean, but also the median and the standard deviation. So the standard deviation, and we think we have a slide on this, but the standard deviation, if you're not acquainted with it, describes how dispersed the data entries are around the mean. So if we have a small standard deviation, it means that all the observations that we have are right around the mean. It's all pretty tight around the mean. And if we have a large standard deviation, it means it varies, has a lot of variability. Okay, and this kind of statistic is helpful for us in trying to understand a particular data set. Okay, we want to know just how variable it is. If it's highly variable, then it might not be good for predicting what's going to happen in the future. If it's got low variability, well, unless the process that generated these observations has changed, probably something like the mean is going to be a pretty good guess at what the values are going to be in the future. Okay? So it turns out that if we want to calculate the median and the standard deviation, we have to do more than just keep running totals. And what we're going to see is that the handy solution to this is to keep our entries, our observations, whatever you want to call them, in a list. Okay? That's where we're headed. So the median, what's that? The mean is the simple average. We've already calculated that. The median is the data value that splits the data into equal sized parts. So for the data 2, 4, 6, 9, 13, the median is 6. Since there are two values greater than 6 and two values that are smaller than 6. Okay, so it is the number that divides the series of observation. If you sort them into order, it's the middle entry or the middle observation. Okay. One way to determine the median is to store all the numbers, sort them, and identify the middle value. Well, it's just what I said. Very good. I'm glad the slides agree with me. The standard deviation is the measure of how spread out the data are relative to the mean. If the data are tightly clustered around the mean, then the standard deviation is small. If the data are more spread out, the standard deviation is larger. The standard deviation is a yardstick to measure or express how exceptional a particular value is. Okay, that's a value in the series. Okay, now here's where we get kind of math poisoning. Okay, and if you have a math aversion, just take a breath here. Okay, and we're going to talk our way through it, and then of course the code doesn't have all these symbols in it. So here's how we calculate the standard deviation. It is the sum of calculations that we do over the whole list of values. Okay, so we're going to calculate it in a loop. All right, and we're going to calculate it using code that's a whole lot easier to read than this. Okay, so it has a symbol, this X with the bar over it, which he comes to call X bar. That's the mean. Okay, uh, X sub I represents the ith data value, and N is the number of the data values. So N is the total of all the data values. Let's say we've got 30 of them. So N's going to be equal to 30. If the third one is 25, then it, it, X subscript 3, is equal to 25. Okay, so what is this expression here? Well, this says that here's what we want to do. We want to take the mean, and we want to subtract each data point, each observation, each entry. And then we want to, so that gives us the difference between between our data point and the mean, okay? And then we square it. Okay, and the difference between our data point and the mean is called the deviation of an individual data item from the mean. Okay, so go a little bit further. The numerator in that big equation that we saw is the sum of these squared deviations across all the data. So we run through all the data. Well, first we figure out what the mean is, right? And then we run through the data a second time. We take a second pass. And we figure out what each of the deviations is from the mean. And then we square it. Okay? So it says, suppose our data was 2, 4, 6, 9, and 13. The mean is 6.8. So the numerator of the standard deviation is all those differences, the difference between 2 in the mean, 4 in the mean, 6 in the mean, all those differences squared and added up, that's 74.8. Okay. And this, I think, so let's go a little bit farther. As you can see, calculating the standard deviation not only requires the mean, which can't be calculated until all the data is entered, but also each individual data element. Because what we're really trying to measure is how dispersed is the data. Is it very tight around the mean, or is it highly variable? So we need some way to remember these values as they are entered. We're going to a list. Okay? Applying lists. We need a way to store and manipulate an entire collection of numbers. We can't just use a bunch of variables because we don't know how many there will be. Okay? And this is pretty typically what you want to do. If you have a series of things, and it's not always going to be the same length, the general approach to it would be to use a list, because the list could do a good job of holding the series when there's one element in it, when there are 10, when there are 10,000. So what do you need? You need some way of combining an entire collection of values into one object. Well, we've already learned about one. It's the list. Okay? So Python lists are ordered sequences of items. For instance, a sequence of n numbers might be called S. And you could think of the contents of S as S0, S1, S2, S3, up to N, Sn minus 1. So why do we start to count with 0? Well, these are the indexes. Okay, so if S is a list, then S0 is the first element of the list. And if it's n long, then the last one is going to have the index n minus 1. So specific values in the sequence can be referenced using these subscripts. Now, subscripts is a math term, okay? Subscripts is a term that's used in some computer languages, but in Python, when we're using lists, the number that helps us to identify which of the elements we want is called an index. Okay? So by using the numbers as subscripts, mathematicians can succinctly summarize computation over items in a sequence using subscript variables. So this actually describes a summing loop. Okay. So we want to say that we want to sum S sub I from I equals 0 to I n minus 1. Okay. Now, do I need you to understand that mathematical notation? No, not really, because what I really want you to understand is how we're going to do this with the Python to sum up the sequence. All right? So suppose this sequence is stored in a variable s. So we're going to have a variable s, which is a crummy name for a variable, but he's decided to use it. So we could write a loop to calculate the sum of the items in the sequence like this. So we would say that the initial sum is equal to 0. And then we could say for I in range n, so that's going to go from 0 to n minus 1, sum gets assigned the current sum plus the element at s index I. Right? Okay, so that's going to work just fine. So nearly every computer language has a sequence structure like this. In a lot of the earlier computer languages, they're called arrays. Okay? We don't have arrays in Python. Python has a list that has that satisfies the need for an array without having a lot of the drawbacks that they had in these arrays in earlier programming languages. So, but you may hear the term array and wonder what that would be closest to in Python, and your answer would be, it would be closest to a Python list. So a list or array is a sequence of items where the entire sequence is referred to by a single name, a variable name. And individual items can be selected by indexing. So in this case, the name is S, and we are using index I, assuming that that's a variable that has a proper integer in it. In other programming language, arrays are generally a fixed size, meaning that when you create the array, you have to specify how many items it can hold. Now, this is why we don't have arrays in Python, okay? Because the number of times where the number of cases where you know ahead of time how many inputs you're going to have is really a few. Okay? Generally speaking, you start to interact with the client. and the client would like to interact until they feel like they're done. So if you ask them ahead of time how many inputs they're going to give you, quite often they don't know. And of course, if you're reading the inputs out of a file like we've done in preceding chapters, well then you have to read the entire file to find out how long it is. Okay, so arrays, which are old-fashioned compared to lists, have that drawback. Okay. Arrays are also generally homogeneous, meaning they only hold one type of data. Okay. Now this, I would point out that this isn't the drawback that people often think it is, because even though our lists it can hold heterogeneous entries, okay, typically the lists that we create hold homogeneous entries. They're all entries of the same type. Okay, so it's a drawback, but in practice, not that big of a drawback. But the fact that we can use a list to hold heterogeneous things, okay, I'll take it. Every once in a while, that's a capability that we're going to need, so we'll take it. So compared to these old-fashioned arrays from other languages like C, okay, or PL1 or COBOL or Fortran, Python lists are dynamic. They grow and shrink on demand. Okay, so we don't have to worry ourselves as the programmer about how long they are. Okay, all that happens kind of under the hood. It's part of the mechanics of Python, and we don't have to worry about it. Python lists are also heterogeneous. A single list can hold arbitrary data types. Python lists are mutable. Well, we learned that when we did the experiment to see whether a called function could actually change the contents of a list as experienced in the calling code, and we found out that it can, because they're mutable, they're changeable. Okay, so it turns out that there's a lot more that we can do on a list that we've already learned about. Okay, so what have we learned so far? Well, we've learned this one down here. Okay, we've learned that if we use the name of the sequence, the name of the list, and then we have some kind of index value after it, that we will actually access that item or element in the list. We also know that we can get the length of the list, the current length of the list, by calling the function len and passing it the list. Okay. We also know about slicing. Okay, so we can use slicing expressions to get a subset of the list. Okay. We also know that we can do iteration over a list. So we can say for variable in sequence, and we can iterate over a list. It turns out there are three other operations that we haven't done yet. You can concatenate lists, so you can glue them together by just using the name, the variable name for one list, a plus, and the variable name for the other list. That's pretty handy when you want to do that. The other thing is that you can take a list and give a repetition factor, and we'll see that in a minute. And then the last thing that you can do is that there's a test where you can ask if a certain value is in the list, okay, and you'll get back a true or false. Okay, so let's take a little bit more of a look at the things we can do with lists we haven't already learned. So it says, except for the membership check, we've done all these things before. The membership operation can be used to see if a certain value appears anywhere in a sequence. So if we have a list that holds the values 1, 2, 3, and 4, if we ask the question, is 3 in list, the answer will be true because 3 is a value that's in the list. Okay, so the summing example from earlier can be written like this. We initialize the sum to 0, and then we can say for x in S, although I've got to say that, again, in my mind, neither x nor S are good variable names. Okay? Computer scientists might like to do this, but good working, practicing programmers want more meaningful variable names than X or S. Okay? And then so we're going to iterate over all the members of the list, all the items in the list, and we're going to add them to the sum, which is initially 0, but you'll have the sum of the items in the list when you're done. Okay? Unlike strings, lists are mutable, and we've already seen this. So we have a list, and we ask for list index 3, which is going to give us the fourth one. Okay? 4, we get 4. And then we say list 3 equal hello. And now the list holds 1, 2, 3, hello. Now this really illustrated a couple of things. One was that it's changeable. And the other is that it can hold heterogeneous types. They all don't have to be ints at the same time. We've got 4 values, int, and string. And then we can say list index 2, we want to assign a 7. So index 2 is going to be the third one. 1, 2, 3, that's 3. That's going to become 7. So then if we display the list, we've got 1, 2, 7, and hello. Okay, so pretty much what you'd expect. So a list of identical items can be created using the repetition operator. So let's say you wanted to create a list and you wanted it to contain all zeros, right? So maybe this is a list of values that are associated with, say, all 50 states or something like that. So you can say the list is going to be called zeros. And we say that it has a single member 0 times 50, and we're going to get what's going to result from that is a list of 50 ints that are zeros. Lists are often built up one piece at a time using append. Okay, so if we look at the preceding slide, 2 back here, okay, and we look at code like this. Sorry, let's try. It does not want to cooperate. Okay, we look at code like that. Okay, that's a hard-coded list. Oh, okay, and a hard-coded list is very nice for these teaching examples, but in more typical working situations, we want lists that come from either the user entering them at the console, or perhaps in a web application, or reading them from some kind of a sequential text file, right? So in those cases, let's go back. In those cases, uh, we're going to build them one piece at a time. If we're getting them from the user, right, one at a time from the console, then every time we get one, we're going to want to append it to the list. Okay, how could we do that? Well, we have a list called nums, which is not such a bad name. Not great, but not bad. And then every time we get a new input from the user, apparently we're getting floats, okay, we say nums append x, okay, while x is holding our float. And so what it's going to do is it's going to add it right onto the back of the list. So here, the nums list is being used as a kind of accumulator, starting out empty, and each time through the loop, a new value is tacked on. Okay, so this is a pretty common pattern that we follow. Okay. We could also be doing this if we were getting them from a file. We might read a line of a file, and we might get the value from that, and we might append it to the list. Okay. So it turns out that lists have a bunch of methods that we haven't been using. Well, we did use a couple of them, and they're really cool. Okay, well, let's look. Well, we've heard about append. Okay. Sort is really the coolest thing. So we say sort, and we might give some information about the order. We'll talk about that before we get done with sort. The list. A comparison function may be passed as a parameter. Okay, so with some objects, it's obvious how we want to sort them. Or if we want to do them in sort of an intuitive way, we don't have to give information about how to order the sort. But we do have the option to do that, and we're going to do that a little later in this chapter. Reverse. What does this do? Well, it takes the order of the items on the list and it reverses them. So if it says A, B, C, D, then it changes the order so that it's D, C, B, A. This is a cool one. We can, on the list, we can call index and pass it a parameter or argument. And what happens is it returns the first occurrence of X. Very nice. What if we want to insert something into a list? Well, on that list we call insert. Okay. We give it the index where we want to insert it, and then we give it the thing that we want to insert. Here we're calling that X. Here's one that we've already used in our course when we want to get a count of the number of items that are equal to the argument in the list. So we were counting just in the last chapter in our exercises, we were counting color names. Okay. Remove. It deletes the first occurrence of X. Pop. It deletes the ith element of the list and returns its value. So this is a situation where we not only want to retrieve it, but we want to consume it. And this is often used for some kind of a queue. Okay, so we have a bunch of things that are waiting in line. The English will, the British will say, when they're waiting in line, they're queuing. They're waiting in a queue. Okay, not Americans so much. Okay, but Americans will say that they're waiting in line. But the science of managing lines of things that are waiting is called queue management. Okay, and there's sometimes when we want the last in to be the first out. There are times when we want the first in to be the first out. And how can we do this? Well, we can do this with some code, but how do we add things to the list? Well, either with insert or append. If we want to add it to the end, we can append it. If we want to insert it in a particular position, like the beginning, we can use insert. And then how about if we want to consume either, say, the first one or the last one? Well, we can use pop. Okay, so pop is very good for getting values from a list that we want to consume when we're doing queue management. Okay, so here are a bunch of examples. So we have a list with all these values. We say we want to append a 2. Where does it go? It goes on the back end. We have a bunch of we have a list with a bunch of ints, and we say we want to sort it. How does it sort it? Well, by default, it sorts in ascending order of ints. Okay, so we've got 2 1s. They show up together. Okay, if we say that we want to reverse list, it puts it in the reverse order. Okay, now remember, because lists are mutable, we're actually changing the value of the list. Okay, we are actually rearranging these sub-objects in the list. And we say that we want the index of 4, so that's at 0, 1, 2. It's a 2. We say that we want to insert 4 hello. Okay, so 0, 1, 2, 3, 4 hello. It goes in the 5th one. Okay, we ask for a count of 1. Okay, and we get 2. 1, 2. We ask to remove 1. What's left? Well, only one of the ones is left. Why? Because we got rid of that. We say that we want to pop value 3. So value 3 is 0, 1, 2, 3. That's the one that actually is 3. Okay, so we get the value 3, and then when we list it, the 3's been consumed. Okay, and again, this process of placing values either at the head of the list or at the tail and consuming them with pop, that's really good for these queue management applications. Most of the methods don't return a value, they change the contents of the list in some way. Lists can grow by appending new items, and they can shrink when items are deleted. Individual items or entire slices can be removed from a list using the del operator. Del for delete. Let's see that. So we have a hard-coded list, and we say del mylist 1. So that's 0, 1. Okay, so the 26 is going to be deleted. And then afterwards, if we ask the value of mylist, well, the 26 is not there. Or we could say del mylist 1 to 3. So that would have been 0, 1, 2, 3 isn't even on here. Okay. So you would think that that would get Python upset, but apparently it doesn't. It seems to be pretty tolerant of asking to delete something that's not actually there. So the result is that the 0th one is not deleted, and we're left with 34. A del isn't a list method, but a built-in operation that can be used on list items. Okay? It's a lot like the operator that we use to find out the length of a list, len. Okay? No, I'm sorry. Len is the function. So this is actually I don't think we have a corollary to it. It's just a command all by itself. And so you're not passing the list in parentheses. You just say del, and then you say what you want to delete, and it goes and it deletes it. So it's unlike the length in that respect. So it's not a method, it's not a function, it's a built-in operation. Kind of different from a lot of things that we've seen before. Be right back. Okay, so let's talk about basic list principles. A list is a sequence of items stored as a single object. Okay, it's a complex object. Okay, it's an object that has sub-objects. Okay, the significant properties of the list object are how many members it has and what the members are, what the items are in the list, and what order that they're in. Okay? The sub-objects themselves are responsible for controlling their own value. Items in a list can be accessed by indexing, and sublists can be accessed by slicing. Well, yeah, we've talked about that. Lists are mutable. Individual items or entire slices can be replaced through assignment statements. We've seen that. Lists support a number of convenient and frequently used methods. Lists will grow and shrink as we need them to. It turns out that because of all these cool properties and the methods or the operators that we just explored, lists are good for solving a host of problems. Now, we've used them for a lot already, and now we're going to go explore even some more applications of kinds of problems that we can solve with a list. So, what about our statistics problem? You remember that our problem was that we need to calculate the mean. We did that a couple of chapters ago. That's not that hard. We can keep a running total. So we don't have to keep all the individual items in a list. Okay? What about if we want to calculate the median, which is the middle value? Do we need to keep all the items? Yeah, we do, because we have to know how many there are and we have to sort them into order before we can figure out what the middle value is. Okay, so we need a list for median. Okay, what about standard deviation? Well, we need to calculate the mean. And then 2, we need to look at each of the items on the list and do some calculations to show how much it varies, okay, from the mean. And then there's a kind of a gross summary calculation that calculates the standard deviation for the whole set of data. Okay, so the mean, don't need a list. The median, need a list. Okay. Standard deviation, need a list. Okay. So what we're going to do is we're going to rewrite the earlier program to use lists to find the mean. Okay. Let's do it. Okay, so let's write a function called getNumbers that gets numbers from the users. We'll implement the sentinel loop to get the numbers. An initial empty list is used as an accumulator to collect the numbers. Okay, so this is another sense of accumulator in that accumulating a list of things is not quite like accumulating a sum, but you can kind of see that when you're accumulating a list of things, you just keep tacking things on the end. So again, it's a related pattern. The list is returned once all the values have been entered. Okay. Now, this is a pretty cool thing. Okay. I'll tell you what I like about this. This is really one of the first uses of functions to we've taken a bunch of code that we could have coded in the main, okay, but in terms of textbook examples, there haven't been a lot of instances of code that we could have coded in the main that we decided instead we were going to factor it out into a function. Well, here we're going to do it. Okay, so from the main we're going to call get numbers. Okay, and we're going to build a list, and then we're going to return the list. Okay, so how does main get access to the list that we build? Well, it's the return value of get numbers. Okay, so let's look. Again, what I have called this nums. No, I wouldn't. I would have called it numbers. But nums equals the empty list. Sentinel loop to get numbers. I guess we're getting them from the console. Xtir is a badly formed Python variable name that says we're getting the value x as a string. So we just input it. And then we say while xtir isn't equal to the empty string, we haven't hit the empty string sentinel value, convert the string value of x into a float, x, and then we're going to append x onto the list of nums, and then we're going to prompt for input again. Okay, now this is a classic setup where we have a while and we have a priming read. Okay, so we have a priming read, then we do the while not at the end. And then, of course, when you do this kind of a construct with a priming read and a while, you have to remember to have another read at the bottom of the body of your loop. Okay, classic design. And then after we've accumulated all those and the user has hit just enter to say that they're done and we get the empty string, then we return nums already populated. Okay? So using this code, we can get a list of numbers from the user with a single line of code. In main, we could code, well, some higher level function, we can code data, which is a horrible variable name, equals get numbers. Okay, why is data a horrible variable name? Well, because all variables refer to data. You know what I mean? It's like having a word that you call word. Well, I guess it's a word, but can we be more descriptive about what this is? Okay. Okay. So now we need a function that will calculate the mean of the numbers in a list. The input is a list of numbers. Well, we just got one back, so we have one. And the output is the mean of the list of numbers. Okay. So the mean is called nums. Okay, this is we're expecting to get a list. Okay, so what are we going to do? Well, we're going to accumulate the sum. So we set the sum equal to 0, and then we do a for in, and we accumulate the sum, and then we divide. Okay, now I just want to point out that by this point in my class, you should be not you should not be writing code like this that could accidentally divide by 0. Okay, so for instance, I would want you to catch that and to return some reasonable value or to raise an exception. Okay, because we don't want this thing just to die in front of the user. All right. All right. So this calculates the mean, and it returns an expression that is the calculation of the mean, provided that we have some numbers to do that with. Okay? All right, that looks good. The next function to tackle is the standard deviation. In order to determine the standard deviation, we need to know the mean. Should we recalculate the mean inside of std_dev? Okay. Should the mean be passed as a parameter to the function std_dev? Well, in my world, the function would be called standard deviation, or something like calculate standard deviation. Okay. These little naming schemes are traditional, but they're not good professional programmer practice. As you can see, I harp on them all the time. I'm sorry, I can't control myself. Okay. Recalculating the mean inside of the function is inefficient if the data set is large. Well, that's not even the major problem with it. As a general principle, we're going to try to eliminate any duplicate code. Okay? Why is that? Well, because we don't want to write it twice. Okay? We don't want to test it twice. Or sometimes it's not twice, it's 3 and 4 and 5 times. But even more than writing it and testing it, when we go to maintain it, you can accidentally forget to change one of them. Okay? And it's very difficult. If in fact you know that the programmer who wrote the program that you're trying to maintain, if you know that they religiously squeezed out all code duplication, if you find the formula, you'll know that if you change that, well, then you're changing the formula for whatever it is, in this case, the mean. Okay? But if you code it in more than one place, a classic example is that you go back and you're asked to change the program. You go, oh, here's the calculation for the mean. You change it, and it turns out that there were 2 or 3 other sets of codes that calculated the mean because they were duplicate code, and now you've got wrong answers coming out of the code. Pretty bad. Okay? So more than efficiency, okay, squeezing all duplicate code out of your program it's a stronger principle than even efficiency. Okay, since our program is outputting both the mean and the standard deviation, let's compute the mean and pass it to standard dev as a parameter. Now, there's a third solution that I'll talk about in a minute. So Let's look at that. Okay, so here's what I like about this code. I don't like the name so much, but std_dev maybe isn't so bad. Um, it's not a proper Python function name. Okay, a proper Python function name would be a combination of lowercase letters and underscores to separate the words. Okay, so not only is it short, but it kind of defies our naming standards. Okay, but what I like about here is it says, oh, we're getting two parameters in. We're getting nums, which is the list of numbers, and we're getting x bar. What's x bar? This is what the crazy mathematician who wrote the book thinks that we should is a good name for the mean. Look, if it's the mean, call it the mean. Okay, call it mean. Okay, so nums, comma, mean. Okay, so the sum of the deviation squared is going to be a float, which we initialized to 0. And now we're going to go through all the items in nums, and we're going to calculate the difference of the mean minus that num, that observation, that piece of data. Okay, that's the deviation. And then we say the sum of the deviations squared equals the prior sum plus the deviation times itself. Okay, well, this is nice, but of course you'll remember that if you're on my team, you don't leave expressions that you need to understand the precedence of operators in order to do. So I would have put a set of parentheses around dev times dev. Okay. In fact, or I would have said dev star star 2, which would have been a way to square it, but that's fine. Okay, I'll be happy if you just put an extra set of parens around that part of the expression. And then when you have summed the squares, then you take the sum of the deviations squared divided by the length of nums minus 1, and that is the standard deviation. Okay, now what I really like about this is that we've taken probably the hairiest math that I've really asked you to do, and we have put it into a function. Okay, now a couple of things there. One is that it's only calculated in one place. Two is you only have to know how to do it in one place. One aspect of this is if you can't figure out how to do it yourself, if you forget this formula, you can go read a book and figure this out. You can figure it out from the Zelle book. Or you can ask a colleague, or you can Google it. Okay? So one of the things that you want to do with almost anything that you don't understand, but certainly the math, is to contain it in individual functions. Hide the calculations in one spot, and then you have to figure it out just one time. Okay. The other thing I'd like about here is that you know that the standard deviation takes the mean and the list of numbers. Okay. Now, I just want to point out that for those who are interested in software design, okay, do we want to recalculate the mean here? Well, here's what I would have done. I would have just passed nums, okay? And then the first thing that I would have done in here would be to call the other function that calculates the mean. So I'd only have the code in one place. Okay, that's fine. But certainly calculating the standard deviation implies that you have to know the mean, but it would be okay to calculate it in line 1, provided that you didn't duplicate the code for calculating the mean. You just would call the function. I just would call it right here, in which case you only would be passing in nums. So do you need to make that change to this? No, you don't. I just I wanted to pass on a little wisdom. So the summation from the formula is accomplished with a loop and accumulator. Sum dev squared stores the running sum of the squares of the deviations. We don't have a formula to calculate the median. Okay. We don't have a formula, we have a recipe. Okay, we have an algorithm for it. We have a way to do it. It's just not something that is you can have an algebraic formula for. Okay, we'll need to come up with an algorithm to pick out the middle value. First, we need to arrange the numbers in ascending order. Okay. Second, the middle value in the list is the median. That's if we have an uneven number of entries in the list. If we have an even number, what's the middle value? Well, if the list has an even length, the median is the average of the two middle values. What do we mean by the average? Well, we mean the mean of the two. We mean value 1 plus value 2 divided by 2, right? Okay. Now, one of the things I love about the Zelle book, I'm grousing about the variable names, and I'm grousing about this and that. So I have to remember to tell you things that I love. I love that he breaks into pseudocode all the time, okay? Because pseudocode, especially as a beginning programmer, will serve you very well. So the pseudocode for what he wants to do to come up with the median, sort the numbers into ascending order. If the size of the data is odd, the median is the middle value. Else, the median is the average of the two middle values. Return the median. Oh, great. Now, I think that's a lot easier to understand than the code that we're going to see in a minute. Okay, so here's the code for this. Okay, so what do we get in? Well, we get in the list with the numbers, nums. Okay, so what's the first thing we do? We sort it. That's it. Okay, is it going to go into the right order? Do we have to worry about the order? No, we don't. Why? Well, because it's a list of these, we know it's a list of floats, and we know it will sort them into ascending numeric order, which is just what we want, okay? The size is the length of nums. So we say mid-pos, which is, I guess, the middle position, equals the size integer it divide by 2. And then here we're going to use the modulo operator. So if we say if the size modulo operator 2 equals 0, well, then we know that it has an even count, okay? So we say that the median is the mid position plus the mid position minus 1 divided by 2. So that's the average. Else, it's the mid position. And then at this point, we populated median and we return it. Pretty cool. Okay, so that's pretty straightforward code. Again, I always like the variable names a little more descriptive than these, but I'll take them. Okay. So with these functions, the main program is pretty simple. It is. Okay. And here's where we get back to, and this is why I really like this example. Why did we call it main? We called it main because our main code is going to be in it. Now, in almost every example we've had so far, we can fit all of our code into main. So it doesn't really illustrate the fact that once our program gets bigger, we need to. It's going to make sense to factor parts of it out and put them into their own functions, like get numbers, like mean, like standard deviation, like median. And so here, look how this reads. It's very summarized. Okay, we print a polite message about what we're doing. Okay, and then we get numbers and we put it into a horribly named variable called data. We call mean with that list called data, and we get the mean and we put it into a mathematically named a variable called x bar, and then we call standard deviation with the data list and the mean, mathematically called x bar, and then we call median on the list with the data, and we get back the median, and now we've got the mean, the standard deviation, and the median just in variables, and we print them: mean, standard deviation, median. Okay, and what I always say is when we properly factored out the code, that the code, the higher level code, in this case in the main, it should read like a children's book. You just, you read through it, and there's like, it's immediately clear what's going on. And this, I think, meets the reads like a children's book test. So I really like this. Okay. So he says here, statistical analysis routines might come in handy sometimes. So let's add the capability to use this code as a module by adding the test at the bottom. If dunder name equal if dunder name equal dunder main, then we want to do the main. Okay. Generally speaking, from my perspective, if we want to build modules with shareable code, we probably ought not be putting solutions into their main. Okay, when we build shareable code, and if we put them in some kind of a module that's going to act like a library, if we're going to put some main code in there, I don't know what it's going to do. Perhaps it's initialization code, or it could be test code. Although when you really learn a formal testing framework, that's not where you put your test code. But this idea that he has here, that we can kind of have our cake and eat it too. We can use this as kind of one-off application program, and then we can reuse the sub-functions as kind of a library module. I think that's, in terms of modern software engineering, it's a bit of a wacky idea. Okay? But it will work, because if in fact you load this as a module and you import it, it will not execute the main. Okay? It just will give you access to the functions. So let's take a breather here for a second, and I'll be right back. I suggest that you do the same. Okay, we're back. So we're going to shift gears a little bit. We're going to do something a little different with lists that relates to Chapter 10. Now, this is kind of fancy for us because we haven't covered Chapter 10 yet. But keep the faith. I will cover the parts of Chapter 10 in a minute that we're going to need. So all the list examples that we've looked at so far have involved simple data types like numbers and strings. So we've had ints, we've had floats, we've had strings. Okay. We can also use lists to store more complex data types, like our student information from Chapter 10. Okay, so let's, before we jump into that, I just want to say this. You can have a list of any type. Okay, now what types are there? Well, there are number types like int and float. There are text types like string, right? So we have those. There are a whole bunch of complex data types that are typically instances of a class. Okay. Now, have we used any of those yet? Well, we probably have, but I can't think of one offhand. But what we're going to learn, what we learn about in Chapter 10 is how to create custom classes. Okay. And so we can create a custom class, and from that, we can create instances of that class, and those are custom objects. Well, it turns out that that's really a powerful thing to do. All right. So, how will you use these class-based objects? Well, uh, it fits into kind of two categories. One is that as you learn about more of the kind of wider capabilities of things that have been built around Python, you'll find out about a whole bunch of classes that have been created for your use. Okay, and you'll learn how to create instances of them and to use their capabilities. Okay, have we done that yet? No, we haven't done that yet. In order to learn how to use a custom class, we usually create a really simple one. And in Chapter 10, Zelle creates a really simple class, and it's called student. Okay, and so here I've got this. I've got this as a got this in a project that I'll make available with our content for this chapter. It's called Demonstrations to Supplement Zelle 3E Chapter 11. So this is where you can find this code. Okay. So we can take almost any kind of entity that we're interested in the world. A student, we can track students, courses, automobiles, cities, desks, any kind of class of object in the world that you interact in your information system, you can make it. If there isn't a general kind of a built-in class for it, like integer or float or string, you can create a custom class. Okay, and people do this all the time. So here, Zelle has created one for student. Well, where is that? Well, he has it hidden in one of the chapter 10 code examples called GPA. Okay, and in it he does uh, really two things. One, he provides the code for the student class. Okay, and two, he provides the code for essentially testing the student class. Okay, and then in the end, he puts the code for testing the student class primarily into main. Okay, and then at the bottom, instead of just having an invocation to main, he says if dunder name equal dunder main, then run main. So if in fact we load this thing all by itself, well, it runs the main code, which essentially tests the student class. Okay. So what's in the student class? Well, a class is so a student class is a type. Okay, so the student class can be used to represent any student. Okay, and it has property and behavior. Okay, all classes do. What kind of properties do students have? Well, according to this definition of the class, every student has a name. They have a number of credit hours that they take and called hours, and they have earned a certain number of credit hour points, which he calls quality points. Okay, so they've got three pieces of data that they carry around with them. Okay, and they also carry around behavior. And what kind of behavior? Well, calculate the GPA. So how do you calculate the GPA? Well, you take the Q points and you divide them by the hours, and you get the GPA. Okay. So, in fact, another file that I included in your in this supplemental project that you can download is his data file for testing. So these are the students: Henry Adams, Susan Computewell, Denny Dibblebit, Jim Jones, and Frank Smith. And a lot of these people, it's kind of hard to calculate their GPA, but Susan Computewell has done especially well. So she's taken 100 credit hours and she's earned 400 quality points, which gives her a 4.0 grade point average. So for Susan Computewell, when we ask for the GPA, it's going to divide the 100 by 400. The 400 by 100, and it's going to get a 4.0. The other people are going to be not quite so even. Okay. Okay. So what have we got here? Well, classes have again, they hold data. They've got fields. Okay, in this case, the fields are name, hours, and Q points. And they've got methods. The key method for this class is GPA, which of course I would have called determine GPA or calculate GPA, but he called it GPA. Okay, typically the name I have for methods, I want more action oriented. Okay, GPA sounds like the name of a piece of data, not a piece of action. Okay. It turns out that there is an interesting approach that are taken in some Python classes that if you want to get the value of the data items, there are methods that have a particular name in order to get them. So if you want to get the name, you can call this thing called a getter, get name, and it returns the value of the name for this instance. If you want the hours, you call get hours. If you want the Q points, you call get Q points. If you want to calculate the GPA, I would have called this calculate GPA, so you would call calculate GPA. In our case, it's called a GPA. We just call GPA. Okay? So how would we use a class like this? Well, I created a I created a Python file that is a little bit better named. Okay, it's called use student class. So how would we use it? Okay, well, all my code's in the main. Okay, and if I want to use the student class, I either have to define it in my file, or I have to import it from another file. So I import Zelle's from the code I showed you before was in a file called gpa.py. So I say from GPA import student, a capital S because it's a class. If we go back to GPA, we'll see that student, again, has a capital S, right? Okay, so how do we create a new instance of that class? Well, we do it like this. It's called calling the constructor or instantiating a student, creating an instance. You give a variable name, and then we assign the value, the name of the class, okay, and then we pass in the values we want to populate this instance with. Okay, so the name, the hours, and the quality points. So we pass in Mary Q Scholar, 100 hours, 400 the quality points. Okay. Now, how do the values get from the ones we pass in, and how do they get into the right fields? Well, that's part of the magic that we're going to learn when we get to chapter 10. Okay, so don't worry about it for now. So what happens here? What happens if we print the value of a variable that refers to an object that's a student object? Well, if it's a very simply made object like this, we're just going to get a pretty useless, let me toggle the rest of this code into comment. We're going to get a pretty useless representation of the object that relates to Mary. So let's do that. Let's run it. Okay. And it says it's a GPA.student object, and it's at a certain memory location. Well, that's not very useful. Okay. We're eventually going to learn that we can create a method called dunderstring, which will always give us a string representation of this instance. Did he do that in chapter 10? No, he didn't. Will we do it when we cover it? Yes, we will. Okay. So for right now, just printing and passing the variable name that points to this instance of student gives us a pretty useless rendering of the object. Well, what if we call the getter methods? Okay, let's uncomment those. So I'm going to print a blank line after the useless version that we have here. And then we're going to print the name, the hours, and the Q points. Okay, now some of you may have already seen that it's actually possible to refer to the field names directly. and not call the getter methods. Okay. In chapter 10, he calls the getter method, so we're going to do it the way he did it in chapter 10. So if we print Mary.getName, we should get Mary Q Scholar. If we print Mary.getHours, we should get 100. This is a float, so it's probably going to be 100.0. If we print Mary.getQPoints, we're going to get 400.0. So let's do that. Let's run that. And here they are. So these are the properties. These are the values of the field for this instance of student. Make sense? Okay. Well, what if we want to get the GPA? Well, we just call the method GPA. So how do we do that? Well, we say we want to print, and then my string says Mary's GPA is, and then I call the method GPA on the object pointed to by Mary, and I get back the GPA. So let's see that. And there comes her perfect 4.0. That's how that works. Pretty nice. All right. So it turns out that we can, in a list, we can put ints into a list. We can put floats into a list. We can put booleans into a list. We can put strings into a list, or we can put instance of custom classes into a list. Either the custom classes that we create, or maybe classes that are not true user custom classes. They're part of this whole Python infrastructure. Okay, so we learn how to use another class. We can put an instance of any class into a list. So here we created one instance. Okay. All right, so that's it. That's all we need to know from chapter 10 in order to get on with the show. So let's look at a list of records. So one typical application of something like this is, let's say we wanted to keep data records on students. Well, we create a class student, which has a field for each of the data items we want to track for a student, and has a method for each of the operations we want to do. For instance, we don't want to store the GPA if we can calculate it, because it's redundant information that can get out of whack. And so instead of having a field for GPA, we have a method, GPA, that calculates the GPA on the fly. Okay, so we could do that for anything that we want to keep records on. Okay? So let's go a little farther. Sorry. All right. So our grade processing program read through a file of student grade information and then printed out information about the student with the highest GPA. Forgot to show you that. So let me do that. We've got that. So we're just going to fire that up. There it is. Where's the grade processing program? Well, he has it packaged with the class. So this main that he has a file of the data for students that he reads in. Where's that file? We already saw that. Okay, so we got 1, 2, 3, 4, 5 students, right? And so he reads them into a list, and then he processes the list. This is the standard where he's looking for the highest, and then he finds the highest, and then he prints information about the highest. So what happens if we run this? Well, we run it, and they enter the name of the grand file. The data file is students.date. So let's make this a little bigger so we can see it. Students.date for data. And it says the best student is compute well, Susan, hours 100, GPA 4.0. And we had already looked. Susan compute well has a 4.0 average. That's implicit in these data. Okay, so that's the program that we're talking about. All right, and you can run that if you want because I've given you both the data and the program. So our grade processing program, GPA.py, read through a file of student grade information and then printed out the information about the student with the highest GPA. A common operation on data like this is to sort it, perhaps alphabetically, perhaps by credit hours, or even by GPA. Okay, so the stuff that we've sorted so far have all been simple types. They only have one value in them. Okay, if you sort ints, it's pretty easy to figure out how to sort them. You sort them into ascending order. And floats and strings, you sort them into alphabetical order. Okay. What about these more complex objects like students? Well, it turns out that we can sort them. Okay. We just have to give the sort method a little more information about how we want it to be sorted. And we can even sort these custom objects. It's pretty darn cool. So let's write a program that sorts students according to GPA using the student class from the last chapter, the one that we just saw. Okay, what does he gives us? He gives us pseudocode. Don't I just love them? So get the name of the input file from the user. Read student information into a list. Sort the list by GPA. Get the name of the output file from the user. Write the student information from the list into a file. Oh, so he wants us to sort the file into GPA order. Now, the coolest thing about this is what? The file doesn't have GPA in it explicitly, okay? You have to call the GPA method on a student object that you built from this file in order to figure out the GPA and to sort it into that order. So we're going to be able to do that with our list. Pretty cool. Okay. Let's begin with the file processing. Following code reads through the data file and creates a list of students. Okay, so we get the file name, then we open that file, and then we create an empty list of students. Okay, and we say for line in file students append make student line. What's make student? Well, that was a helper method that we had in GPA. So make student did the following thing. It took the input line, it split it into its parts. Okay, it split it on the tab character. Okay, and it got the name, the hours, and the cue points, and then it created a new student object with the name, the hours, and the cue points. So that's just a helper method that we're calling there. Okay, good. So we're using the make student helper method from the GPA program. So we'll need to remember to import the student class. Oh, okay. Well, we did that when we just used the student class, so not too surprising, huh? Let's also write a function to write the list of students back to a file. Okay, we didn't have that in the program from the chapter 10. So what does it do? Well, it does the opposite. Um, instead of reading these things, uh, and reading the records and creating a student object, well, instead of that, this, when we write the file, we have a list of student objects, and we iterate over that, and we write a line to the output file for each of the students. Okay, so how does this work? Well, he needs the list of students and a file name, and he opens it for writing, and he iterates over the students for S in students. And what does he do? Well, he prints out using a formatting string. So, so we have the first value, then a tab, then another value, then a tab, then the third value. And what does he populate it with? Well, get name on the student object, get hours on the student object, and get points on the student object. And where does he put it? He puts it in out file. And then when he's done with all that, he closes it. Okay? So this is in computer science ease. When we read in the file and turn them into programming objects, that's called deserializing it. This is called serializing it. We take these internal objects and we turn them into text on the outside. And of course, text is serial. We write it one character after the next. Okay, so this is where we serialize the students, and the other code that we saw is where we deserialize the students. So using the functions read students and write students, we can convert our data file into a list of students and then write them back to a file. All we need to do now is to sort the records by GPA. That's pretty cool. In the statistics program, we use the sort method to sort a list of numbers. How does Python sort lists of custom objects? Okay. To make the sorting work with our objects, we need to tell sort how the objects should be compared. We can supply a function to produce the key for an object using, and so we can have the name of our list dot sort, and then we have a keyword parameter here. We say key equal, and then we have the name of a function that we want it to call. Now this is not a function call itself. This is just the name of the function, so it has no parens on the end. Okay, it's going to turn out that it's even easier than this, and we'll see in a minute. So to sort by GPA, we need a function that takes a student as a parameter and returns the student's GPA. So what would that look like? Okay, so we could say use GPA. So we get past a student and we return a student GPA. We can now sort the data by calling sort with the key function as a keyword parameter. So we can say data, which is a pretty poor name for a variable, dot sort equal, and then saying that the key is our function that we created, use GPA. Okay, that's great. It turns out we're doing too much work in the end. So will that work? Yes, that will work. Oh, okay. Now this would be nice to do if we had some really fancy way that we wanted to sort it. Okay, but we already know how to get the GPA, so this is a pretty trivial function. Okay. Um, Notice that we didn't put the parens after the function name, and that's because we use the parens when we're calling the function. We don't want to call it. We want to pass it to the sort method, and then the sort method is going to call it. Now this is a pretty fancy Python feature. We can pass variables. We can pass the fields on objects, and we can actually pass methods as well, or functions. Okay. Because of that, we don't have to write our own function to get the GPA. We can point to the method that's in the class that returns the GPA. So how do we do that? Well, this is easy. We say key equals class name dot method name. Do we have a paren? No, we're not calling the method. We're just identifying it so sort can call the method. Okay? We've never really done something like this before, where we pass the name of a method to code that was going to call it on our behalf. Okay? And then here's the program. Okay? So let's find the part where we sort it. The part where we sort it is right here. Now, I don't know why I could never get this thing to highlight what I want. Yeah, it's right here. So we say data.sort, and we have to tell it that on each of the things that is in data, we want to call the GPA method of the student class. And that's going to make sense because the things that are in the list are all instances of the student class. Now, what did we do before that? Well, we printed a polite message. We asked for the file name. We called read students. We did the sort. What do we do after that? Well, we get the output file name. We call write students. We print a polite message, and we're done. Okay. Now, something that he does here that I'm going to complain about is that he has this if test kind of indicating that we might use this Python module as a library module. We're never going to use this as a library module. So this kind of goofy code, I think, is useless. I think you just want to have the call to main out here all by itself and not hanging off of this silly if. Okay? So that's it, right? So this really illustrated a number of things that I'd like to review for a second. One, that we can create custom data types for really anything that we want. And it turns out to be a great way to represent records about things in the world that we want to keep. So if we want to keep information about students, we can create a student class, and it can represent all the data that we're interested in about that student. You notice it doesn't have home address or mother's maiden name or anything like that, because that was not within the scope of our current interests. Okay. Could we have included those things? Well, if they're within the scope of our current interest, we definitely could have. So we can we can use these custom classes, which we're going to learn about more in a couple chapters, and we can create instances of them. We can take data from a file where one line represents one instance, and we can build them up into instances of things like a student. In computer science, we call that deserializing the file. And then we can put all of those student objects into a list that turns out to be a really handy way to process them in our program. We can sort them even by GPA. And if we wanted to sort them by name, we would call the getter on the name. If we wanted to sort them by by hours, we would call the getter on the hours. But if we want to sort them by GPA, we just call the GPA method. And then in the end, what did we do? Well, we took the list and we serialized it into a file. So again, each of the items that was on the list it turned into one line in a text file. And this is a pretty typical pattern that you'll see, and it's kind of nice that we finally had a chance to see it. So that's it for part one. That's all we're going to talk about lists. I'll be back in part two to talk about dictionaries, which are the other data collection type in Python that is very popular and you're definitely going to want to know about. See you soon.